Picture a patch of wetland right in the heart of the Congo Basin.
Okay.
It covers just like 4% of the surrounding area.
Which is pretty tiny in the grand scheme of things.
Right, it's tiny. But buried underneath that relatively small swamp is this layer of incredibly dense peat, and it's holding 30 billion tons of carbon.
Wow. Yeah, 30 billion.
Which is, I mean, it's the equivalent of all the carbon stored in every single tree across the other 96% of the entire basin combined.
It's staggering when you actually look at the numbers.
It really is. And if the global climate shifts just enough to, dry it out, that tiny 4% patch of land turns into a 30 billion ton compost bomb.
Releasing the equivalent of, well, basically 3 years of total global human carbon emissions.
Yeah.
Just from one single highly localized area.
Today, for you listening, our mission is to understand the actual mechanics behind scenarios exactly like that one. We're going on a deep dive into tipping points in the Earth's climate system.
And it's such an important topic right now.
Exactly. And the goal here isn't to, induce panic or make you doom scroll through the audio. Our objective is to give you a clear, mechanically grounded understanding of the physics and the biology driving all these headlines you see.
Right, because there's a lot of noise out there.
There is. So we're going to demystify what a tipping point actually is. We'll trace the specific vulnerabilities scattered across Earth's ice, oceans, and forests. And then we'll look at the terrifyingly fascinating ways these massive planetary systems interact with each other.
The stakes for understanding this architecture are just immense. I mean, a major 2022 study in the journal Science established that exceeding just 1.5 degrees Celsius of global warming above pre-industrial levels, that is, could trigger multiple tipping points simultaneously.
Simultaneously, wow.
Yeah, we're looking at the potential collapse of major ice sheets, the abrupt thawing of permafrost, and, the wholesale transformation of rainforests.
Right.
But the key to grasping this isn't just knowing what might change. It's understanding why these massive planetary systems can transition so radically and often irreversibly.
Okay, let's unpack this because the term tipping point gets thrown around constantly, right?
Absolutely, all the time.
And usually with this implication of an overnight catastrophe, like pushing a glass off the edge of a table.
Right, the classic analogy.
Yeah, 1 second it's fine, then the next second it's just shattered on the floor. But the physics of a planetary climate tipping point operate a bit differently, don't they?
Yep.
If we cross a tipping point today, the world doesn't literally change tomorrow.
Very differently, yeah. The glass falling off the table is actually a pretty misleading visual.
Really? How so?
Because it conflates the trigger with the transition. So in climate mathematics, a much better way to visualize a tipping point is, well, imagine bending a thick piece of industrial plastic.
Okay, I'm picturing it.
If you apply pressure to it, it bends, and if you let go, it just snaps right back to its original shape.
Which would be like a resilient climate system.
Exactly. But if you bend that plastic past a very specific invisible angle, its yield point, the internal molecular structure, fundamentally alters.
Ah, so even when you stop applying pressure, it doesn't snap back.
Right. It has permanently found a new deformed state. We call that bifurcation-induced tipping.
Bifurcation-induced tipping. Okay, so crossing the threshold just locks in the destination. The speed at which it bends, or, the ice melts, is a completely separate timeline.
That distinction is paramount. The moment you push past that structural yield point, the tipping point is officially crossed.
But the transition takes a while.
Yeah, the actual physical transition into the new state might take decades, centuries, or even millennia. I mean, the Greenland ice sheet could cross the temperature threshold that essentially dooms it within our own lifetimes, but the sheer mass of the ice will take thousands of years to physically melt away.
So the trigger happens now, but the transition plays out over generations.
Exactly, unless, of course, we've done the plastic too fast.
Wait, what happens then?
Which brings us to rate-induced tipping. This occurs when the environmental conditions change so rapidly that the system simply cannot adapt or migrate to keep up.
So it just breaks.
Essentially, yes. Even if the absolute temperature hasn't reached that theoretical yield point yet, the sheer velocity of the warming forces a sudden shift. It's the difference between slowly pushing a piece of plastic until it deforms and violently bending it so fast that it just snaps in half.
Wow. Okay. So now that we have a grasp on the underlying math of the deformation of the system, let's look at the first major physical structures feeling that pressure.
The cryosphere.
Right, Earth's ice.
Yeah.
Because these are universally considered the first potential dominoes to fall. Let's start with Greenland. Why is a block of ice that massive so inherently fragile?
Well, it comes down to a localized atmospheric mechanism called the melt elevation feedback.
Melt elevation feedback. Okay, break that down for me.
Think of the Greenland ice sheet as essentially a continent-sized mountain made entirely of ice. It reaches miles into the sky, and atmospheric physics dictate that air at higher altitudes is colder than air at lower altitudes.
Right, like hiking up a mountain, it gets colder at the top.
Exactly.
Which means as global warming melts the top surface of the ice sheet, the overall height of that ice mountain physically drops.
And as the altitude of the surface drops, that surface is now sitting in lower, warmer air.
Oh, I see.
So the warmer air accelerates the melting process, which drops the elevation even further, plunging the surface into even warmer air.
It's a self-feeding loop.
It is a self-feeding, inescapable loop. The ice sheet literally shrinks itself down into a warmer climate.
That is wild. And researchers actually found physical evidence that this exact feedback loop has tipped before, didn't they?
They did, yeah. It's fascinating.
From what I read in the sources, they drilled a 1.4-kilometer ice core in Greenland. And by analyzing the subglacial sediment at the very bottom, they discovered that the ice sheet melted away entirely at least once in the last million years.
Which proves it's a proven vulnerability.
Right.
It suggests the threshold for complete collapse is highly sensitive, potentially even lower than the maximum global temperatures the Earth reached during that previous interglacial period.
Okay, so let's travel to the opposite pole, down to the West Antarctic ice sheet, or WAIS, as it's called.
Yeah.
The architecture here is completely different from Greenland, right?
Completely different. The ice there is over 4 kilometers thick in places, but it's sitting on bedrock that is mostly submerged below sea level.
Wait, hold on. If the bedrock is below sea level, that means the ocean can literally get underneath the ice sheet and melt it from the bottom up. Is that why it's a runaway effect?
It's even more dramatic than that. The ocean water doesn't just get underneath, it fundamentally destabilizes the structural anchor.
How does it do that?
Well, over millions of years, the unimaginable weight of that 4-kilometer thick block of ice actually compressed the Earth's crust. It created a deep subglacial basin.
So the ice is sitting in a bowl.
Essentially resting in a massive underwater bowl, yeah. And the specific location where the ice detaches from the bedrock and begins floating on the ocean's surface, that's called the grounding line.
Right, the grounding line. And because that grounding line is sitting on a downward slope leading to the bottom of the bowl, any melting pushes it backward into deeper water.
Exactly. Warm ocean currents erode the edge of the ice, forcing the grounding line to retreat. And because of the bowl's slope, retreating means moving into deeper water.
And deeper water means more of the ice is exposed.
Yes. Deeper water exposes a taller cliff face of ice to the ocean heat. That increased exposure causes it to melt faster, which pushes the grounding line even further down the slope.
It just keeps feeding itself.
It's a mechanism called marine ice sheet instability. Once that grounding line starts retreating down the incline, gravity and thermodynamics basically guarantee a self-sustaining, irreversible collapse.
That's wow. Okay, before we move on from the ice, there's a vital nuance regarding the Arctic Sea that we should cover. Because we constantly see headlines about summer Arctic sea ice disappearing. But mechanically, that is not currently classified as a tipping point. Why is that?
Because a tipping point requires a transition into a new, irreversible, stable state.
Okay.
The loss of summer sea ice in the Arctic is ecologically devastating, sure. And it absorbs massive amounts of solar heat because dark water reflects less sunlight than white ice.
Right, the albedo effect.
Exactly. But the long, dark Arctic winter is still profoundly cold. It's cold enough that the ice can recover and refreeze every single year.
So the system bends, but it bounces back.
Right. It hasn't reached bifurcation.
But the Barents Sea has.
Yes, the Barents Sea is the crucial exception here. It is warming at an astonishing rate, up to 7 times faster than the global average.
7 times. That's insane.
It is. The water there is absorbing so much heat during the summer months that the winter temperatures are no longer sufficient to extract that heat and refreeze the surface.
So the winter ice just doesn't come back.
We are looking at the permanent loss of winter ice. That is a true tipping point. The system loses its ability to bounce back entirely.
Okay, so all this melting ice from Greenland and the Barents Sea, it doesn't just raise sea levels and vanish. It pours trillions of tons of fresh water directly into the North Atlantic Ocean.
A massive influx of fresh water, yeah.
And that fundamentally alters the fluid dynamics of the planet.
Which brings us to the AMO Sea. the Atlantic Meridional Overturning Circulation.
The AMOC is arguably the most critical cardiovascular system on Earth.
Cardiovascular system, I like that.
It really is. It is a staggering global conveyor belt of water, and it's driven entirely by differences in water density.
Let's map out that plumbing system for everyone listening. It starts at the equator, right?
Roughly, yes. So the sun beats down on the tropical Atlantic, heating the water. And that warm surface water is carried north by currents like the Gulf Stream toward Europe.
Right, moving the heat north.
But as it travels north toward the Arctic, two things happen. First, it cools down in the frigid air. Second, a lot of the water evaporates, but the salt stays behind.
The salt concentration goes way up.
So by the time this water reaches the coast of Greenland, it is extremely cold and intensely salty.
And in oceanography, cold and salty means heavy.
Right, dense.
Very dense. That incredibly dense water sinks deep into the ocean abyss. This massive, continuous sinking action in the North Atlantic acts like a colossal pump.
Pulling everything else along with it.
Exactly.
Right.
As millions of cubic meters of dense water plunge to the ocean floor, it creates a void at the surface, which physically pulls more warm tropical water north to replace it. That downwelling is the engine that keeps the entire global conveyor belt moving.
Okay, so now introduce the melt elevation feedback of Greenland that we just talked about.
Yeah.
You are suddenly dumping astronomical volumes of fresh, highly buoyant meltwater directly into that downwelling zone.
Yes. You are severely diluting the salinity of the North Atlantic.
Like watering down a hearty soup.
That's a great way to put it. The water becomes fresher, which means it becomes lighter. It loses the density required to sink.
And if the water stops sinking, the pump stalls.
The conveyor belt grinds to a halt.
If that plumbing system shuts down, what happens to the heat distribution of the planet?
The thermal balance goes into shock. Without that conveyor belt bringing tropical heat north, parts of Europe could experience up to 10 degrees Celsius of rapid cooling.
10 degrees, that's a massive shift.
It would be devastating. Arable farming in places like Britain or Scandinavia could become economically impossible, but the global impact is far more severe than just Europe getting cold.
What else happens?
The AMOC dictates the position of the intertropical convergence zone.
Which is the thermal equator, right?
Right, the thermal equator that drives the planet's major monsoon systems. If the AMOC stalls, that rain belt shifts drastically southward.
Oh, wow.
Billions of people in West Africa, South America, and India who rely on those monsoons for agriculture would face unprecedented drought.
And we are seeing early signs of this exact same dynamic at the South Pole, too.
We are, unfortunately.
Antarctic meltwater is pouring into the Southern Ocean, freshening the water there and disrupting the southern overturning circulation. So the dense Antarctic bottom water is being diluted, weakening the lower, deeper ocean currents while the upper wind-driven cells actually strengthen.
The planetary engines at both poles are simultaneously sputtering.
All connected.
It is. Now, while a total collapse of the AMOC is currently considered unlikely to happen within this century, the physics dictate a severe weakening regardless. Current projections estimate a slowdown of 24 to 39%.
So the ocean conveyor belt weakens, the heat distribution of the planet gets lopsided, and that directly displaces the tropical rain belt.
Right, exactly.
Suddenly, the rainfall that terrestrial ecosystems rely on is happening somewhere else, which takes us out of the water and directly into the world's most vital forests, the Amazon rainforest.
Yes, the Amazon.
The scale of the Amazon is difficult to comprehend, but the biological engineering is even more staggering. I mean, the Amazon literally generates half of its own rainfall.
It operates as a continent-sized biological water pump through a process called evapotranspiration.
Evapotranspiration.
Okay.
How does that work?
Well, the billions of trees in the Amazon absorb groundwater through their roots and transpire it out through their leaves as water vapor.
Like the forest is sweating.
Basically, yes. And this massive release of moisture into the atmosphere creates immense, localized, low-pressure systems. Those low-pressure systems physically suck in more moist air from the Atlantic Ocean.
It's incredible.
The moisture condenses, falls as rain, waters the next section of the forest, and the trees pump it right back into the air.
It is a self-sustaining weather machine.
Yeah.
But 20% of the Amazon has already been systematically deforested, right?
Which critically damages the pump. If enough forest is removed, whether through direct human deforestation or climate-driven drought, the evapotranspiration cycle falters.
The trees stop sweating enough moisture.
Exactly. The low-pressure suction drops, and the downwind regions simply stop receiving rain. The forest dries out, triggering a massive dieback.
So it just dies off.
The complex, layered rainforest canopy collapses, and the ecosystem transitions into a degraded, dry savanna. And once the biological pump is gone, a savanna cannot generate enough moisture to ever transition back into a rainforest.
The plastic has permanently snapped into a new shape.
Precisely.
That structural transformation is terrifying. Which brings us back to that visceral hidden detail we discussed at the very beginning of the deep dive, the cuvette central peatlands in the Congo Basin.
Right, the compost bomb. This represents one of the most volatile rate-induced tipping points on land.
Just remind us, what exactly are peatlands?
Peatlands are essentially waterlogged bogs where dead plant matter accumulates over thousands of years, but doesn't fully decompose because it's submerged in water, cut off from oxygen.
So it's a massive carbon vault.
Yes.
30 billion tons of carbon locked in just 4% of the Congo Basin's area.
But the local climate surrounding the Cuvette Centrale is already dangerously close to the limit of what can sustain a wetland. It is significantly drier than the peatlands in the Amazon or Southeast Asia.
Okay, so what happens if it crosses that limit?
If shifting global rain patterns or increased temperatures dry this swamp out, the water table drops. The peat is suddenly exposed to oxygen.
And when oxygen hits thousands of years of undecomposed organic matter, the microbes wake up.
Aerobic bacteria begin breaking down the peat at an explosive rate. This microbial frenzy releases staggering amounts of carbon dioxide and methane directly into the atmosphere.
Just a massive release.
And the decomposition process itself generates intense heat, which dries the surrounding peat even further, sometimes causing the ground to literally spontaneously combust. It becomes a compost bomb.
Wow. And we have an even larger version of that compost bomb sitting in high latitudes, don't we? The Arctic permafrost.
We do. The permafrost holds roughly twice as much carbon as is currently circulating in our entire atmosphere.
Twice as much.
As the Arctic warms, the frozen ground thaws, the dormant microbes wake up, and they begin feasting on the organic matter, venting methane, which is profoundly more potent than CO2 into the air.
Which dramatically accelerates the very warming that sawed the ground in the first place.
Exactly.
You know, this isn't just a list of isolated regional problems. We aren't looking at separate files in a cabinet here. This is a single, heavily interconnected engine. What happens when we zoom out and look at the causality between all these systems?
You're touching on the frontier of current climate research right now. Cascading tipping points.
Cascading tipping points. So dominoes.
Exactly. Through advanced network model analysis, we can map how crossing a threshold in one specific element fundamentally alters the physical environment of another element, pushing it past its own yield point.
Trace that cascade for me. How did the dominoes actually fall?
Well, let's start at the top. Global temperatures rise, pushing the Greenland ice sheet past its melt elevation threshold.
Okay.
Greenland melts, pouring billions of tons of fresh water into the North Atlantic. That fresh water dilutes the salinity, which stalls the downwelling pump of the AMOC ocean current.
Right, the conveyor belt stops.
With the ocean conveyor belt crippled, global heat and rainfall patterns shift drastically.
The thermal equator moves south.
Exactly. This new, altered atmospheric circulation starves the Amazon rainforest of moisture, triggering a dieback that turns the biological pump into a dry savanna.
Okay, so the Amazon is down. What about the north?
Simultaneously, the stalled ocean currents trap warmer water in the higher latitudes instead of dispersing it, which accelerates the thawing of the Arctic permafrost.
Oh, wow.
The permafrost and the drying peatlands release massive vaults of ancient carbon and methane into the atmosphere.
Which supercharges the global greenhouse effect, making the planet even hotter, which melts whatever is left of the ice even faster. It's a closed-loop planetary chain reaction.
It really is. And this network of interactions exposes a massive flaw in how we often discuss climate targets.
What do you mean?
Well, policymakers frequently rely on the idea of a temporary overshoot. The logic assumes we might briefly surpass 1.5 degrees of warming, but later, using advanced carbon capture technology, we'll just pull carbon out of the air and bring the temperature back down to a safe level.
Like an undo button. But the math of a tipping cascade doesn't allow for an undo button, does it?
Not at all. Network models reveal that even a temporary overshoot increases the risk of triggering these irreversible tipping cascades by up to 72%.
72% just from a temporary overshoot.
Yes, because once you bend the plastic past its yield point, it doesn't matter if you subsequently remove the pressure. The internal structure has already transformed.
The damage is done.
Once the fresh water stalls the AMOC, pulling carbon out of the air 50 years later won't jumpstart the ocean currents again. The cascade has a memory.
So, synthesizing this journey for everyone listening, We started by understanding the fundamental physics of bifurcation, how stability is slowly eroded until a system seeks a new state.
Right.
We looked at the self-shrinking ice mountains of Greenland and the vulnerable subglacial bowls of Antarctica. We traced that melting water into the Atlantic, watching it dilute the dense, salty downwelling pump that drives our global weather.
The AMOC.
And we saw how a stalled ocean stops the biological water pumps of the Amazon while waking up the microbial compost bombs in the Congo and the Arctic. It is a staggering mechanical web.
It highlights the sheer scale of the Earth system. But if we connect this all back to you listening, the most important takeaway is actually buried in the timelines we established at the very beginning.
The difference between the trigger and the transition.
Yes. The triggers for these thresholds might be crossed in the near term, but the physical transitions, the complete melting of the ice sheets, the total transformation of the rainforests play out over decades, centuries, or even millennia.
So there's still time.
The speed and severity of those transitions are entirely dependent on how much pressure we continue to apply. Human agency is the defining variable here. The emissions decisions made in this current decade dictate the absolute maximum temperature the system experiences, which directly determines exactly how many of these systems are pushed past their yield point.
We are entirely in control of how hard we bend the plastic. And I want to leave you with one final provocative thought regarding the absolute extreme limits of our climate.
Okay.
When discussing tipping points, there is a popular apocalyptic scenario that gets brought up a lot, the idea that human emissions could push Earth into a runaway greenhouse effect, turning us into a replica of Venus, where the oceans literally boil and evaporate into space.
It's the ultimate catastrophic visualization, for sure.
But mechanically, it is a localized impossibility. According to atmospheric physics and the data analyzed in these sources, a Venus-style runaway greenhouse effect has virtually zero chance of being triggered by human activity.
Yeah, no chance.
Basically zero. For Earth's climate to physically boil the oceans, the sun itself would need to naturally brighten by tens of percents. Astrophysically, that stellar evolution won't happen for another 600 to 700 million years.
That's a relief, at least. Earth's climate is exquisitely sensitive, and we can absolutely push it into a state that is deeply hostile to human agriculture, coastal infrastructure, and the global economy. But the laws of physics prevent us from turning it into Venus.
We aren't going to boil the oceans into space. The planet will remain. The only question is what kind of internal equilibrium it settles into. Something to ponder as you look up at the clouds today, realizing that every single system, from the ice to the ocean currents to the sweating leaves of the rainforest, is connected by an invisible thread.